Today, we are going to learn one of the most important things that we're going to do in this unit, and that is locating an epicenter. This is actually the first of two videos on this. The first video, we're going to go through why it works. The second video, we're actually going to work on the math of plotting an epicenter together. So I would like everyone to be open to Notes Pack page 2829. Get that, get a pencil and get a calculator. And always good to have is a highlighter or a colored pen or pencil to take some notes as we're going through this. So if you don't have that stuff, pause the video and go get it and then come on back. All right, so locating an epicenter, we have done the basis of this. We have learned about P&S waves. We learned about the Porsche and the Subaru. And we're going to need to kind of go back to that and remember our time math and remember how to use the Earth Science reference tables, the P&S wave graph, and remember our green sheet method. We are going to be practicing this a lot over the next couple of days. And your goal is to get fluent at this. Remember that this is station 2 of the lab practical that we should be taking in June, but we shall see. So what do we need to know? To locate an epicenter, you need to measure the seismic waves recorded at 3 different seismic stations. And you need a P&S wave time travel graph, which is the ESRT's page 11. Look at that number right there, that number 3. Everyone see how that is a special color. That is purple. You need 3 seismic stations to do this. Not 1, not 2, but at a minimum 3. More is better, less is not okay. And you're going to learn why that is in a second. When you know your distance to epicenter, you can draw a circle around your seismograph, so your seismometer. It's called a seismic station, a seismograph station. Seismograph stations are where seismologists work. It's where seismographs, aka seismometers, are located. And those instruments record the seismic waves as they approach the station and give you the P arrival and the S arrival. And with those 2 times, if you remember correctly, you can determine everything else about the earthquake. And what happens is that seismologists get together and they share their data and they're able to locate the epicenter, which is the place on Earth's surface right above the focus. We're going to draw 3 circles, and where they intersect, that is going to be the location of the epicenter. All right. Remember the rules. P waves always arrive before S waves. The farther you are from the epicenter of the earthquake, the greater the time difference between the arrival of the P and S waves. Okay, so the farther you are, the greater the lag, or the worse the Porsche is going to beat the Subaru's butt. Remember that? Knowing the distance from the epicenter of 1 or 2 seismograph stations is only going to give you a rough area of where the earthquake occurred. To find the exact position of the epicenter, you must have, at a minimum, 3 seismograph stations recording. Count them, 3. Did I mention that the number was 3? You can have more. You can have more, but no less. And that is a reference to Monty Python and the Holy Grail. And if you don't know that movie, maybe while you're home, you can watch it if your parents say it's okay. So if you have data from 1 station, what do you need? How many more stations do you need? If you only have 1, you got it. You need 2. If you have data from 2 stations, how many more stations data do you need? That's right. 1 more. You need 3 stations at a bare minimum. Okay, so how does it work? I'm actually going to leave this and I'm going to go to here. Okay, so here's an animation of how this works. Okay, so I'm going to pause it as we go. Here's seismograph station A. Here's seismograph station B. Here is an earthquake. It is the same earthquake, even though there's 2 different little drawings here. Same exact earthquake. Okay, there's your P wave, your S wave, and your surface waves reaching each station. There was a 2-minute lag here. There was a 4-minute lag there. Okay, now on this diagram, I'm going to pause it. On this diagram, we have 3 seismograph stations, 1 in Denver, 1 in St. John up in Canada, and 1 in Lima, Peru. The lag time at Denver was 3 minutes. The lag time at St. John was 8 minutes, and the lag time at Lima was 12 minutes. Even without this, even if you didn't have this up here, how do you know who's closest? That's right. This was the least lag time. So we know that this was closest to the epicenter. But we also know their arrival time. So we have the P arrival and the S arrival for each station. All right. Now, what we do is we take the lag times and we plot them using our green sheet method on the PNS graph in the ESRT. And by doing that, if there's a 3-minute lag, we know that the station at Denver is 2,000 kilometers from the epicenter. With an 8-minute lag, you're 5,300 kilometers from the epicenter. And with a 12-minute lag, you're 9,000 kilometers from the epicenter. So what, Ms. O'Gorman? So we know the distances from the epicenter. How does that help us? That's the part we haven't done yet, and that's what we're getting to. So when you know your distance to epicenter, you can plot your distance to the epicenter. So I'm in Denver, okay? I'm in Denver, right here. That's my seismograph station. I know that I am 2,000 kilometers from where the earthquake occurred. So what do I know? If I only have one station's data, where can the earthquake be? Here, there, or over there, here, there. Ooh, up in Alaska. Ooh, Canada. Ooh, it could be in the Pacific Ocean. It can be anywhere on that circle because all this seismograph station knows is, I'm 2,000 kilometers from the epicenter. That's all they know. Then they're going to get some data from St. John's. Well, at St. John's in Canada, they know that they're 5,300 kilometers from the epicenter. So what do you know? The earthquake could be here on the Atlantic. Oh, up in Greenland. Oh, over here in Canada. Oh, wait a minute. They intersect here and here. So what have we done? We've narrowed down the earthquake to 2 locations, either right there or right there, because that's where the 2 circles intersect. But what do I need? I need the 3rd station. I need the 3rd station, which is Lima. Okay, there's your 2 question marks. Now we know. See, now the people in Lima know that they're 9,000 kilometers from the epicenter. That's a radius. So what we're going to learn to do when we get back is we're going to learn how to draw these circles. And I'm going to model it in a little while. Okay? This is what we need to be able to do. We need to draw these circles. Now look what happened. That's where the 3 of them intersect. All right? That's where the 3 of them intersect. There's 3 lines. And if they don't all intersect perfectly, you get a little triangle. And we're using 3 data sets. So this process is called triangulation. It's called triangulation, okay? So that's the process. So I want you to watch this video. This is a quick little video, and it's going to, okay. So here's our seismograph station. It happens to be at the North Pole, whatever. That's not where you would really find a seismograph station, but that's how this looks. But what they're going to do is they're going to plot a whole ton of earthquakes, and they're going to show you
a seismic station will record 10 earthquakes to show how the data fit the travel time graph. The first earthquake occurs about 3,000 miles from the seismic station. P, S, and surface waves leave the hypocenter of the earthquake, and their arrivals are recorded on the seismograms. Only the first earthquake shows the wave front migration, but the arrival of each wave is shown on their respective seismograms. Notice that the farther the earthquake is from the recording station, the farther apart the PS and surface waves are on the seismograms. The red P and blue S waves are body waves that travel through the interior of the Earth. The P wave is fastest because it is a longitudinal or compressive wave, similar to sound waves that travel in the direction of compression. The S waves are 60% slower because they have a shearing motion perpendicular to the direction of travel. The slower yet surface waves roll along the surface of the Earth in an undulating motion. Although there are no continents shown here, so we can place large earthquakes in a random pattern, we will observe an interior similar to that of the Earth. Seismograms reflect the appropriate distances.
So you can see how the P arrival line and the S arrival line were created. Now I know this is not oriented like our graph because our start time is down here. And then they also included the surface waves on this graph. So as you can see, as the distance from the epicenter increases, the lag time between the P and S arrival also increases. This is how seismologists created the P and S wave curve. Okay, so what we're going to do is we're going to look at the next slide. Okay, next slide, please. Thank you. Okay, so here's an example of another earthquake that occurred, it looks like off the coast of California, or maybe on the San Andreas Fault. And there were 3 seismic stations. There was station A, which was 1,500 kilometers from the epicenter, C, which was 8,600 kilometers from the epicenter, and station B looks at over in Hawaii. That was 5,600 kilometers from the seismic station. and from that seismic station, and that's where the epicenter earthquake is, where all three circles intersect. All right. Here's another, just a still of how you can take a difference of 5 minutes, 20 seconds and use the green sheet method, the scrap paper method, and bring it up here. That's where the P wave arrived 5 minutes, 20 seconds ahead of the S wave. And if we go straight down from there, we know that the distance to epicenter is what, my friends? When the lag time is 5 minutes, 5 minutes, 25 seconds, what is the distance to epicenter? Right here. Each line's worth 200, so it is 3,800 kilometers. That's your distance to epicenter. And then on the last slide that we're going to go through, come on. Okay. Here we turned it sideways. Okay, so that's your distance to epicenter. What we're also going to do today is we're going to learn how to figure out what time the earthquake occurred. And that's what we're going to do in paper in one moment. All right, so I hope this was a good explanation of what we're going to be doing, and I'm going to see you in a few minutes in the next video. I want to discard those. Bye.